to hear about this interesting talk.
And thank you for giving me the opportunity to speak here. So my name is Lior Cohen. I'm a new postdoc in the quantum and quantum science and technology group at LSU. But today I will talk about works that we have conducted in the Hebrew University at the Quantum Optics Group, where we encoded information both on polarization and time beam in the same photon. Okay, so as an introduction, I will present how the physical realization of a qubit. Then I will talk about how to encode information both in polarization and in temporal degree of freedom of photons. Then I will talk how to decode information of multi-qubit photon. And if in the remaining time, I will talk about the ongoing work in the lab and open questions that we didn't answer yet. Okay. So when we are choosing our physical system we want to use as a qubit, we need to consider 4 properties, or we need to ask ourselves 4 questions about the system. So, can we do a single photon manipulation or local rotation? Can we do a 2-qubit manipulation, or can we manipulate 1 qubit based on the state of another? How much can we protect our system from the noise, or how decoherence do we have, and eventually, can we read the quantum states from the system? So many physical systems have been used for encoding information, including atoms, ions, electrons, quantum dots, envy centers. Not in this slide. This is not my slide, by the way. For Josephson junction qubits, and of course also photons. We have been using the polarization degree of freedom of photons because it's easy to manipulate and easy to read it out, and photons weakly coupled to the environment, so basically they have almost no decoherence. But we can use any other degree of freedom, including the momentum of the photons, the frequency, the number of photons, and also the time of the arrival. And the key point here is that we can use more than 1 degree of freedom to encode information. That's what all the talk is about. Okay, so how we use polarization as qubit. So a qubit or quantum bit is a superposition of 0 state and 1 state, and we can set the horizontal polarization to be the 0 state and the vertical polarization to be the 1 state, and this is our polarization qubit. We define 4 more states, so P and M are equal superposition of H and V with a plus phase and minus phase, and we also have R and L, the right hand and left hand circular polarization. Any other polarization can be represented as a point in the Poincare sphere or the Bloch sphere. Now, if we want to read out the polarization state, what we need to do is polarization tomography, usually by projecting on an known state. So we can use a polarizer or polarizing beam splitter, an optical device that reflects the vertical polarization and transmits the horizontal polarization. And if we also use wave plates, we can project on the P polarization, M polarization, and the right and left-handed and left-hand circular polarization. So after we project on this polarization, we can find the 4 S parameters, also known as Stokes parameters. And with the 4 Stokes parameters, we can reconstruct the density matrix, like that, where sigma I are the Pauli matrices. More generally, if we want to reconstruct any quantum state, we need d-squared projection, where d is the dimension of the Hilbert space. So for example, for a qubit, d equals to 2, and we need 4 projection for 2 qubits, d equals to 4, and we need 16 projection, and so on and so forth. Okay. For time-beam qubits, it's almost the same story. So we set the undelayed or 0 time to be 0, and tau or delayed time beam to be 1. And again, we can define the plus minus x and other states like that, the same as we did with polarization. And of course, now we have the 2 qubits in one polarization. So the first parameter is the polarization, here it's spin, and the second is the time qubit. So here we have p plus minus, and we can also have an entanglement in one photon. Okay? So H0 plus minus V tau is like 0, 0 plus minus 1, 1, which are 2 Bell states, maximally entangled Bell states. Okay. Okay, so how can we encode information in time beams? We can use scheme like that. So we use a wave plate to set the amplitude of the V polarization, and the V polarization is delayed by some delay line. Then we can combine the V polarization and the H polarization with another polarization beam splitter, and then we can set the polarization, we can encode the polarization qubit here. The problem with this scheme, we have 2 problems. One is that we need to align both special modes to one special mode, and the second problem is that we need usually actively stabilize the phase over here. But we also can use a birefringent crystal for encoding time information, because in birefringent crystal, the horizontal and vertical polarizations propagate in different speeds. So if we take long enough crystal, we can separate the two amplitudes completely, the two polarization amplitudes, the 2 polarizations completely. There is no temporal overlap between those 2 amplitudes. So now the setup is just the same wave plate to set the 2 amplitudes, birefringent crystal, we tilt the birefringent crystal, and that's how we can set the phase between the two states, and after that, again, we set the polarization qubit. Okay, but what with decoding? So we can project the photon onto the 0 time beam, and we can project it on tau time beam, but how can we project on both? How can we detect the photon in 2 different times? Okay, we need it for the reconstruction of the state. So that's a problem, and the solution is by photon bunching on a beam splitter. So for a reminder, just for a reminder, if we have 2 identical photons meet on a beam splitter, both will exit the same port of the beam splitter. This is true only where the 2 photons are identical in all degree of freedoms. So the amount of bunching, the amount of coincidence is a measure for the amount of the amount of the overlap between the 2 photons. Okay, so we are going to use that, and I'll give you some examples. So let's take the encoded photon to be v tau. So we have vertical photon, delayed, all of the information is in the tau time beam. Now let's take the projected photon to be also v tau. Okay, so we use another, let me go one step back. We use another photon to the readout. So we prepare the photon in the projected state, the state we want to project on. And we also can scan the arrival time of the photon, of the ancilla photon. Okay, so now we have the encoded photon v tau, and let's choose the projected photon to be also v tau. So now we scan the delay, and we get perfect dip at 0 delay. Okay? Perfect dip means the projection is 1. So there is total overlap between the 2 photons. We get perfect dip, the projection is 1. If the projected photon is h tau, so the 2 photons are completely orthogonal, there is no dip, which means the projection is 0. What about v0? So if we delay the photon in tau, with tau, we get perfect dip, but we only care on 0 delay. At 0 delay, we get no dip at all. So the projection is 0 as it should be, because v tau and v0 are orthogonal. Okay, so that's how we do it. Let's take some more complicated example. So now we have v plus. So the photon is polarized in v, but in equal superposition of the 2 time beams. And the ancilla photon is also v plus. In this case, we get 2 side dips. We don't care about them. By the way, this is 1 cordon, and this is the dip here is 1 cordon. But we get at 0 delay, we get perfect dip, which means the projection is 1, as we want, of course. And also we got the same result. And if we take v minus, we still get the 2 side dips, because there is no phase dependent when we project the delayed photon with the undelayed photon and vice versa. But at 0 delay, we get no dip at all, which means the projection is 0, and we think about it as destructive interference between the two amplitudes for the bunching term here, and constructive interference of the bunching term in this case. Okay? And also, we can see the result. There is no dip at all, and the projection is 0 as we expected. Okay, we can do the same. We can do the same thing also with entangled states. We take the encoded state to be phi plus Bell state, and the ancilla photon to be in phi plus and minus. And if it's phi plus, we'll get a perfect dip. If it's phi minus, we'll get no dip at all. And in the experiment, we got the same as we expected. Okay, so now we have a dimension of 4. We need to take 16 projections and reconstruct the density matrix. So here we reconstruct the density matrix of phi plus Bell state for P plus and for another entangled state. Okay. So now we should ask what's next. What will be the next step? So it's like a goal to have the biggest Hilbert space you can get, right? So there are two ways we can do it in this system. We can take more particles. In this way, the dimension of the Hilbert state will be 4 to form the temporal qubit, 2 form the polarization qubit, and times the number of particles. But we can also take more time slots, and the dimension will be 2 times the number of time slots. So if we use one birefringent crystal, we get a dimension of 4, and if we use 2 birefringent crystal, we get a dimension of 6. Okay, so what's interesting about the case of dimension of 6 is that the problem of how many mutually unbiased bases we have is not solved yet. So just a spoiler, we don't going to solve it, not today and not now. So what is mutually unbiased basis? Mutually unbiased bases are orthonormal bases that the projection of two basis vectors from different bases is 1 over d. Yeah. Oh,
Ish.
Yeah.
Okay.
I'm on it all the time.
Yeah. Okay.
Okay, so this is the definition of mutually unbiased basis. For dimension of 2, we have 3 mutually unbiased bases. We know what they are. For dimension of 3, we have 4 mutually unbiased bases, and we know what they are. For 6, we know of 3 mutually unbiased bases, and we don't know if we can get more. So this is unsolved problem. Sounds simple, but this is unsolved. So we generated one mutually unbiased basis for dimension of 6. Of course, not the trivial basis, which is h times one of the times. So this is one non-trivial basis. So we generate it in the lab, and this is the results, the experiment and theory, and this is the absolute value of the density matrix. So because of this is mutually unbiased basis, all of the elements are just 1/6. So you see a lot of 1/6 on the board. And so all the information, yeah.
Sorry. In order for mutually unbiased bases to be interesting, don't you need at least two bases?
Yeah, you have the trivial basis.
Oh,
So the trivial basis is just HV and the time bins, and now
you
this
have that
is.
and you have this one. All right, thanks.
And all the information is in the phase of the density matrix, and this is the theory, how the 6 states phases are looking, and we got the same in the experiment. Okay, so there are still things we don't know, and things we want to do. So the first thing, can we encode any state in d = 6? We still don't know if we can do it, and if anyone here can think of how to do it, I guess he will be on the paper, because for now we just have some results. The paper is not written yet. The second thing is, what is the most efficient way to encode those states? So if you remember, we used polarizer to polarizing the polarization to project it to one polarization. So it means loss. So how efficient can we do it with minimal loss? How efficient can we encode the polarization information? And there are things we want to do in the lab. The first one is to use another source of single photon detector, of single photon. So now we use spontaneous parametric down conversion. We want to use a single photon gun. And maybe for the decoding, maybe we can use coherent states, but we don't know yet. And why we want to do it, so we want to increase the generation of states. Okay, so now it's pretty low, it's around 600, a few hundred a second, and if we want to do it in higher speed, we need single photon guns, and of course using more photons. Okay, so for summarize, I've shown you how we can use bioengineered crystal to encode time bin information. I have shown how we can do quantum state tomography of high dimension using photon bunching, and I presented a full state tomography of dimension of 6 and 4. One slide on my previous group. So this is Professor Hagai Eisenberg, our wise advisor and the head of the group and lab. So we had the founder generation, which finishes their PhD a long time ago. I'm part of the second generation with Yuda and Dani. We started approximately the same time, and we finished the PhD at the same time. Now we have a new generation in the lab. So one more. slide about what we are doing. I guess Yuda and Danny work more about things in quantum information. One paper, one work I really like is the generation of one D cluster states from one single photon source. So this collaboration is with Professor Pascal Senelard from Paris Saclay in university in France. Well, I like this work. I think this is maybe one of the best shot we have toward quantum computing. So Hagai has, I think he showed it in LSU last year. So he has a protocol how to generate 2D cluster states and how to do one-way quantum computing with it. So that's just the start. And so that Yuda and Danny work more in the field of quantum information. I work more on quantum metrology with some overlap to quantum information. So for example, you can find online that we use quantum error correction to enhance the sensitivity of phase measurements. That's it, and thank you for
I think we have time for a question. Yeah.
So you mentioned how a single photon can be entangled in polarization and time. How do you extract that entanglement into, say, spatial degrees of freedom that you can use to like violate Bell inequality? Just curious.
Okay. First, if you have the information both in polarization, you can use polarizing beam splitter to separate in space. But so Bell inequality is eventually different projection than what we did, right? So we can do the right projections to get Bell inequalities, and we can violate Bell inequalities with this thing.
Right, but someone might question whether you overcome the locality loophole.
There is no locality loophole because this is in the same place, right?
That's a good response.
All right.
Because it's just so wide open.
No, all right, but it seems that there should be some way to like extract into, like if I want to use the entanglement for quantum key distribution, right? Then you would have to figure this out. Shouldn't it be possible?
Okay, so if you want to use, so I guess if you want to use it for quantum key distribution, what you need to do is you need to entangle it with another particle, okay, and send one of them to one place and the other to another place, and then you have bigger dimension, so you have more mutually unbiased spaces, so you can increase the security by that.
Okay.
But that's the only thing you can do. You can't use one photon to